Hey there, Calc 3 folks. Back here with another lecture over double integration or multiple integration in general. We are going to take a look at, in this lecture, the case for double integrals over general regions, right? Where we are considering calculating this double integral calculation that we're familiar with, occurring over region R, applied to function f, and happening with respect to the area of R, from a rectangular region for R, and consider the case of defining region R in more general terms, where if we think about how we might state those more general terms, right, the way we might describe R is as follows. And if I bring this up into view, you can see here the way we're going to go about describing R is said here. R is going to be defined as the set of coordinates in two-dimensional space such that, again, our values for x are going to be bounded by the values of a and b, but in this case our values for y are going to be bounded by what we're going to think of as functions of x, right? Function g of x and function h of x, g of x on the lower bound, h of x on the upper bound. In this particular case, when we think about illustrating R would be illustrated as I have here in this graph. Again, we can see region R is no longer a rectangular region, but it is this region of space that exists in two-dimensional space for values of x and y, where x falls between these bounds at x equal to a and x equal to b, which is described by these vertical lines in that space, and y is bounded between the function g of x on the lower bound and the function h of x on its upper bound. All right, we can see here by converting y over into, or its bounds over into functions of x, we have this more general description of R. And we're going to be considering having this surface occurring in three-dimensional space over R, and we might be interested in finding the net volume between the surface and this xy plane over this region of R. And the way we would go about calculating that, right, if we think about that actual value, right, we're going to rely on the following theorem. If I bring that theorem into view, I think I can fit it here. I may have to scroll up a little further. Yeah, I'm going to have to scroll up a little further. If we take a look at this theorem, it does assume that we have this surface in three-dimensional space that is continuous over this region R, right? What we think then of as the double integral of f over R, it is given by this double integral calculation here, where we can see that this double integral, right, is going to happen first. If we go inside the integration here into the innermost integral, it's going to happen first with respect to y. That is going to occur across the bounds from g of x to h of x. And once we evaluate that integral operation, we then come back and evaluate the integral with respect to x over the bounds from a to b. When we evaluate our inner integral with respect to y and evaluate it at these functions of x, the result is going to be a function in terms of x in most cases. So we are going to come back then in the second iteration of integration, perform that integration with respect to variable x. Right. And again, this double integral of our function over this region R, where region R can be defined just as any set of coordinates, right, will always yield the net volume trapped between that surface and the xy plane over region R. What we do take note, folks, here is that we do have a very specific case for calculating this double integral. For the case of a rectangular region in the previous section, we had some options for how this double integral calculation could be arranged. But in this particular case, when R is defined as we have stated in this theorem, the setup for the double integral calculation has to be very specific to this setup, happening on the inside with respect to y across these bounds from g to h, and happening on the outside with respect to x across these bounds from a to b. Right? If we look at an example, right, we might consider the example here for the double integral applied to function f over r, right, where f is defined as the function x plus 2 times x times y plus 4y, and all of this occurring over this region R in two-dimensional space here, right, where x is bounded between the values of 1 and 4, and y is bounded between these functions of x. On the lower bound, it's going to be bounded by 1/3 x, and on the upper bound, it will be bounded by the value of 2 times x. 1/3 x and 2 times x are functions of x, and more particularly, you might recognize them as linear functions of x. If we consider the case for region R and what it actually looks like graphically, right? In this particular case, region R would be illustrated as follows. This would be our description for region R. It is this set of points in two-dimensional space with respect to x and y, where x, we can see here, is bounded between these values of 1 and 4, illustrated by these vertical lines, right, bounding the left and right side of R. And y is bounded between these two linear functions. On the lower end, right, for the case of g of x, we see the function 1/3 x, this linear function that has a slope of 1/3. It rises 1 and runs 3, right, and passes through the origin. This is going to be our lower bound on region R, and our upper bound, h of x, is given by the function 2x. It is also a linear equation with a y-intercept of 0 and a slope of 2, meaning it rises 2 and runs 1, right, in its value. These bounds on region R define this region of space in the xy plane, and what we might be interested in is finding the net volume trapped between this surface and this xy plane that's occurring over this region of R, we say. Right? As for that value, right, if we bring that value into calculation here, into place, right, the actual calculation for that double integral, right, is going to be given by this calculation here. Where following the specific setup we had in the theorem, we are going to be applying this double integral to our function f, where the innermost integration is going to happen with respect to y, and it's going to occur across those bounds from 1/3 x to 2x. 1/3 x playing the role of the lower bound on region R, and 2x playing the role of the upper bound on region R. Once we evaluate this innermost integral with respect to y across these bounds of x, we are going to come back and integrate that result, which will be itself a function of x, with respect to x across the bounds from 1 to 4. All right. If we consider that calculation, right, that first iteration with respect to y is going to produce the antiderivative we see here in the brackets. The antiderivative of x plus 2xy plus y is actually going to be xy plus xy squared plus 2y squared when we take the antiderivative with respect to y. This x is treated like a constant, so it's just going to be y to the first power multiplied by that in its antiderivative. 2xy, the y is going to increase by a power of 2, and we're going to divide by 2. So that produces the xy squared, and 4y is also going to have its y increase to the power of 2, and dividing by 2, 4 becomes the value of 2. Now we're going to evaluate this function at the values of y at 2x, where y equals 2x, and take away from it what we would get when we evaluate this function at y equal to 1/3 x. If we consider the evaluation of that antiderivative, right, with respect to y equaling 2x, we have this result. The result would be 10x squared plus 4x cubed. Whereas when I come back and I evaluate this antiderivative with respect to y, where y equals 1/3 x, I end up with this result over here. We're going to take away 5/9 x squared plus 1/9 x cubed as a quantity. Now, if I do simplify that integrand, right, what's inside the brackets there, that does produce the following polynomial function of x. That is the function 85 ninths times x squared plus 35 ninths times x cubed, which we're now going to integrate with respect to x. And here x is going to increase by a power of 3, and we'll divide by that 3. Here x will increase up to a power of 4, and we'll divide by that power of 4. And when we produce that antiderivative, well, you can see here I've actually simplified it first. I took note that there is a like term of 5 ninths, right? Or, well, I should say a common factor of 5 ninths in each of these terms. So I factored out that common factor. And then I'm considering the evaluation of this antiderivative for 17x squared plus 5x cubed. If I bring that into view now, right, following our fundamental rules of antiderivatives, it does produce this antiderivative, bumping up to 3, divide by 3, bump this power up to 4, divide by 4. I produce this result, which I'm now going to evaluate at 4 for x and take away what the value is at 1. Now, I don't know if I showed that explicitly. Let's see here. Oh, I think I did. Okay. Our final line here I have laid out. At 4, this does produce the ratio 2,432 divided by 3, and evaluated at 1, it produces the ratio 89/12. Take the difference of those two, and you get 3,213 fourths, which when multiplied by 5 ninths does simplify to 1,785 fifths. Now, hold on here. I should actually, I think, say that is equal to that, right? 9 does go into 3,213 evenly, right? I believe that's 375 when times by 5 gives us 1,785 fourths, right? That does not reduce any further. As I noted off screen, region R can be defined in more than one ways, right? It has been defined where x is independent, varying in this closed interval from a to b, and y dependent upon x. What we're now going to consider doing is changing the dependency in our relationship. We are now going to consider the case where y is independent, varying in the closed interval from c to d, and x being dependent upon y, where x now is going to vary between these functions of y. In this particular case, r is going to be defined as follows. It's going to have a very similar setup to what we had seen previous, except for now x is going to vary between these functions of what are going to be functions of y, and y is now going to fall between some constant bounds c and d. And when we think of the illustration here in general, this is the generic illustration of that region R, right? It's this set of coordinates in two-dimensional space where now we see y as being bounded by these constants c and d, illustrated by these horizontal lines, and it's now x that is going to be bounded on the left by function g of y, right, defining the leftmost bound on R, and on the right by h of y, where h of y is defining the rightmost bound on R, right? In this particular scenario, to calculate the double integral, we rely on a similar looking theorem. Right? If I bring that theorem into view, that theorem is stated as follows. Right? Again, we're going to assume we have this multivariable function in three-dimensional space, this surface in 3 dimensions, and it being continuous over this region R where we have this new orientation, y being independent and x being dependent upon y. In this particular case, the double integral of f over r is going to be given by this very specific calculation. What you will note is we have a very specific result here where the double integral is going to be calculated by first integrating with respect to x. In the other orientation, the first integration happened with respect to y. The innermost integration happened with respect to y. In this particular case, they're swapping roles here. So the innermost integration in this setup is going to happen with respect to x first. That is going to have its antiderivative evaluated across the bounds given by these functions of y, g of y and h of y. And that result will produce a function of y, which you can now come back and integrate with respect to y across the constant bounds from c to d. All right? Notice the order of integration here has changed from the previous theorem with the change in the orientation for the description of R. If we consider a particular example, right? I do highlight an example here illustrating the importance of perhaps wanting to consider this orientation versus the other. If you note here, I say consider the net volume trapped between this surface, 4 plus 2x minus 3y, over a region R, where region R is the region bounded by the lines y equals 6 minus x, y equals 1 plus x, and y equals 1. Right, which would be illustrated as follows. Now, I hope I have this illustration right. I think I do. I'm second guessing myself. Did I get it right? Yes, I did. Okay, so this would be the illustration of our region here. Right? Notice region R, right, is the region bounded by these lines. The line y equals 6 minus x, the line y equals 1 plus x, and the line y equal to 1. It's this interior region here. Now, I did not give you a specific setup. I'm allowing you to kind of approach this, right, or wanting to think about this, right, in terms of our two theorems and our two possibilities for defining R. And what I will note is if we consider the first case of defining R where x is independent and y depends upon x, right, we would see the following in terms of the breakdown for R. If you consider that scenario where x is independent and y depends upon x, R would actually have to be considered as the sum of two other regions. What we would note if we consider x to be independent and having to vary between some constant bounds, R's upper and lower bounds, which are going to be defined by that dependent value of y, actually transition from the line y equals 1 plus x to the line y equals 6 minus x right here in the middle of R. Right here at what we might think of as the x value of 2.5 at 5 halves. Right at the value of 5 halves, we actually have two different descriptions for R. One description for R for the left half, and one description of R given by the right half. Right? In this particular case, if we were to define R with x being independent and R being the sum of two regions, R would actually have to be defined as follows, or R1 would be defined as follows. It would be this region of space where x varies from 0 to 5 halves, right in the middle of our graph, and y is bounded on the lower end by 1 and on the upper end by 1 plus x. As for region 2, we're going to see it's the region of space bounded on the lower end by where x is bounded on the lower end by the value of 5 halves. Let's see if I can get the picture here at the same time. Yep. Where x is going to be bounded on the lower end here at 5 halves and on the upper end at 5. Right? And that's intersected with values of y that depend upon x, where y is bounded on the lower end by the value of 1, the constant value of 1, and on the upper end by this function y equals 6 minus x. Right? That calculation as a double integral is going to be a bit more complex. Right? As for actually calculating the double integral of f over region R, if R equals the sum of these two regions, region 1 and region 2, then the way we're going to have to calculate that double integral is as a sum of two individual double integrations. It would have to be the sum of the integration occurring over function, or for function f over region R1 added to, right, the double integration of function, a double integral of function f that's occurring over region R2. These two double integrals results would then have to be summed to produce the overall double integral of function f over this region of R. This region of R where we are thinking of it as the sum of these two previous regions. All right. Whereas, we could consider a different setup. Whereas we could also consider the setup where y is the independent variable and x depends upon y. If we consider this as the setup for our calculation, then R would simply be defined as follows. All right. If I bring my picture down here, what we might do is go ahead and let's copy this and bring this down so we can see this laid out here with our R a little more easily. All right. If I consider defining R in this manner, first thing we would note is that y is varying between these constant bounds here, starting at 1 and at an upper bound of 7/2. Now 7/2 is 3.5. It marks this location, right, where the graph of y equals 6 minus x intersects the graph of y equals 1 plus x. If you set those equal to each other and solve for x, you will find this 2/2, which we used in our previous setup. But plugging that value at 2/2 into either one of these two cases for x, we would reveal our value for y would be at 7/2 or 3.5, right? So 3.5 would be our upper bound right here at 3.5. Our region R would form from y equals 1 to 3.5 in value, right? As for the bounds on x, those are going to be given by functions of y. The leftmost bound is going to come from the curve y equals 1 plus x, but it's going to have to be expressed as a function of y, meaning I'm going to have to solve this for x. Solving this for x, I just subtract 1 from each side, and I end up with x being equal to y minus 1. So that's where I get my lower bound of y minus 1. And for an upper bound, that is going to come from the rightmost bound here, given by the equation y equals 6 minus x. In the case for y equals 6 minus x, again, that is where x is independent and y is dependent, but we want to express this as y with y as the independent variable. So to do that here, I have to solve this equation for x. I can add x and subtract y from both sides, and I would find that x would be equal to 6 minus y. So 6 minus y would then become my rightmost bound here for the value of x. It would be the upper bound on this description of x. All right. In this particular case, if we define R as follows, you can certainly see the definition for R does not involve breaking R into two separate regions, but involves just defining R as this one single region. All right. So when it comes time for the integration, I'm trying to bring this up into view here. The integration would be described as follows. Right. This double integral across or of applied to function f over region R would be this integral calculation here. As our second theorem highlighted, right? This integration is going to first have to happen with respect to x across those functional descriptions of y, well, functional descriptions of x in terms of y, and then is going to have to be integrated with respect to y. We do see that in this setup, right? Our innermost integral is going to happen with respect to x across the bounds given by these functions of y. Y minus 1 on the lower end, 6 minus y on the upper end. Once we find the antiderivative of this statement with respect to x and evaluate it across these bounds in terms of y, the result is going to be a function of y, where we can now come back and perform our second iteration of integration with respect to y, and then evaluate it across the bounds of y from 1 to 7/2. If we consider doing that in this case, I did present this, right? First of all, note this would be a much more efficient calculation method than our first setup. This would be much more efficient than trying to approach the double integral as seen here, right? We would only be performing one double integral calculation as opposed to having to do two here and then add them together. All right? That is going to bring about some efficiency in our calculation. And if we actually think of the value here, if we give ourselves another example of this calculation, right? This calculation is first going to happen with respect to x, and the antiderivative of 4 plus 2x minus 3y with respect to x is 4x plus x squared minus 3xy. When we evaluate that across these bounds from y minus 1 to 6 minus y, taking it at 6 minus y and subtracting this value at y minus 1, for values of x, that does produce this quadratic function in terms of y, where I can now come back and integrate that with respect to y across the bounds from 1 to 7/2, which produces this as our antiderivative, and when evaluated across these bounds from 1 to 7/2, produces a final result of 175/8 units cubed. Right? Folks, this is double integration, right, happening over general regions. These general regions, right, in the Cartesian system, the rectangular coordinate system can be approached in one of two ways. You can either consider defining a general region of R as we have illustrated initially, with x as the independent variable and y dependent upon x, in a situation that might generally describe its region R as illustrated here, or we could consider a scenario where y is the independent variable and x depends upon y, right? In this particular case, y would vary between constant bounds of c and d, and it would be x that would vary between functions of y. In that particular case, we would see an illustration similar to what we saw here, right? With region R being defined by something that's similar to this illustration. Having these constant bounds at the bottom and top of region R, and having these variable bounds in terms of x being a function of y, describing the left bound and the right bound for region R, right? And as the last example illustrates, right, there are scenarios where one setup, right, could produce a less efficient calculation, right, than an alternative setup, right, where that alternative setup might produce a more efficient calculation, folks, right? Again, this is double integration over general regions, folks. I have a couple of videos to present you over these topics that deals a little bit with application. We're going to see a couple more ideas kind of tie into these ideas. All right, so you will see those videos up here shortly, but then we're going to kind of take all of this and move over to the case of double integrals over polar regions. That's going to be some material that's going to come out in section 16.3. What we've looked at up to this point has been 16.1 and 16.2 material. So I hope you're bearing with it, folks out there. I hope you're all right. Hang in there. We're all doing the best we can. and I will see you in the next video. Later.